points.
Tree roll really quick. What do you like coffee shops?
You like what?
Coffee shops?
I mean, they're okay. Not like a big fan of this. We just have Winslow gone. Does anyone know where Winslow is?
Skiing.
Oh, it's tournament. It's championship.
Okay, I'm not doing that.
Okay. All right. Let's do let's look at 20 together, I guess, because that's another one where you're revolving around the y-axis.
Which one, sorry?
20.
Okay.
Today I'm going to cover, I'll do one more example about just where there's two functions, and we're going to revolve that around the y-axis, and then we'll revolve one of these ellipses around the y-axis. 23 is around the x-axis, but same thing. And then we got to revolve around the line, and then I guess I'll save the last one for tomorrow. It's a pretty fascinating question. If you want to look ahead, you can probably figure out what those are actually about. But probably not. So he said.
Definitely.
The next two problems
Good attitude to have.
potentially overwhelming amounts of
It truly is.
Yeah.
Oh, boy.
Please proceed with caution. That's his instructions for the last two.
Please proceed.
I told you guys about George Danzig, right? Probably last year.
I don't.
No members.
Don't recall, sorry.
Forget it.
Oh.
Okay. Well, there's a whole parabola here, but the region is bounded by this parabola and the line y equals 2x. Now, this drawing is not really to scale, but this is y equals
There's a little
2x.
slip
So
in there, but it's okay.
the region hopefully is pretty clear. I mean, I did draw the rest of the parabola. It just doesn't really contribute to the region. So, and this question does just say write an integral for the volume. It doesn't say find the volume. So
I've come to like those.
I'm glad you like it. So let's examine one of the slices. So if this region, now here's a question for you. Do you know why I'm shading it in this way?
Because it's gonna revolve around the y.
It's revolving the y-axis, so the slices are going to be perpendicular to the y-axis. And so if I imagine one of these slices rotating around the y-axis, and I draw that, I would call that a washer. Okay? That makes sense to everyone?
Mm-hmm.
So the washers would have, the hole would be really big for a washer up top, like up at this y value, and the washers would have a small one down here. So, okay, what is the outer radius? What's the radius?
Bad.
It's related to this. It's definitely related to the parabola, but it's not. It's actually the x value of this point, isn't it?
Yeah.
So it's this distance, which is the x value of a point on this curve. So
Just where.
yeah, I got to rewrite this as, first I might go, 4y equals x squared. And so I get the square root of 4y. Do we feel okay about that?
Yeah.
So this distance between here and here, so the center of the washer, everyone understands that's the center of the washer?
Mm-hmm.
I could have mentioned before. I think this kind of clutters up the picture, but some people like to draw the washer on the diagram.
That's really cool.
Do you like that?
Yeah, that's cool.
To some people, it helps them just kind of visualize what's actually happening. So that is the washer. So the outer radius is this point's x value. This point's x value is the square root of 4y. So square root 4y. And then how about the inner radius?
4y minus that.
It's the x value of this point, which is half of y. Do we feel okay about that?
Yeah.
No? So the distance from here to here is this inner radius.
Good.
So the thickness of the disk is dy. And then, a remark here is that a lot of people, they'll look at the disk, and before doing any of this other stuff, they'll look at what's the expression for the thickness of the disk? Well, it's dy, so that just clues you in that every expression you want to get is in terms of y.
Yeah.
Right? So kind of a clue as to why you want to get this and why you want to get this. So anyway, what's the volume of this disk? Well, it's pi times big radius squared minus little radius squared. Okay, times the thickness of the disk, which is dy. We have any questions on where that's coming from? What?
Yeah, why is it square? Why are like entirely square? Yeah, that's
So generally speaking, if you have if you have a disk, the disk has a little radius, call it R2, and a big radius, call it R1, these two radii. Then the area of this is pi times R1 squared minus R2 squared. Now, if you want the volume of a disk, that's just a circular, whatever you call that, a circular donut or something. If you want to turn it into a disk, you just have to multiply that area by the thickness of the disk. The thickness of the disk is dy. So then you say, well, I want to integrate that. I want to get all the volume between where? Why 16? That's the y value where they cross, right? Can we corroborate that? So for example, what's the x value where they cross? We agree with Trey that when x is 8, y is 16 on this curve.
Yeah.
And on this curve, when x is 8, 64 divided by 4 is 16. So we agree that both curves contain the point 8, 16, and then you got to be able to identify, well, if you're moving vertically, you got to go from 0 to 16. So here's the answer. There you go.
Yay.
Now, just being mindful of being prepared for multiple choice quizzes and stuff. The answer is more likely to get written probably, well, it might get written like this, but it might also get written like having pi outside first of all, and then you can simplify this pretty significantly because the square root of 4y squared is 4y, and then this is a quarter of y squared. Okay, make sense?
Yeah.
As you can see, the arithmetic here would be quite a pain in the bottom because you have a y cubed, 16 cubed. Pretty big numbers.
Bigly.
Bigly numbers.
Bigly.
Let's.
What even is?
We are trying to figure out what 16 cubed is.
16, yeah, I don't even remember what 16 squared is.
4,000 something, I think. because 16 is 2 to the 4th. Cube that, it's 2 to the 12th. I just happen to know 2 to the 10th is 1024, so
Big one.
then you go 2048,
I
Happen
4096.
to know.
Big one.
That's just one it's like knowing your times tables, you know.
I mean, you could also.
you finish a
know it
math
by-
degree, you
by
probably know
playing
your
that
powers of 2.
game.
Probably
2048.
Oh,
You
yeah,
know
I
the
don't
little
play that
game?
very often.
Or that video game.
Josie, I will say PT kicked my butt the other day.
Okay.
She had me doing ladder
Two
work,
more
like
examples
counting
for
down
today.
100 by threes. I could not for the life of me. Even
We're
she was like
going
confused. I
to-
was like, where are you? Go on. I started thinking it took like really and I started counting down to 7 and I'm going insane.
We're going to calculate the volume of what happens if you take an ellipse and you rotate that ellipse around. It could be the x-axis or the y-axis. What you guys pick? You want to revolve this around the y-axis? That's 22 is revolving an ellipse around the y-axis.
Sure, 22.
And then 23 is revolving an ellipse around the x-axis. So
Why not? 22.
hopefully if you understand 22, 23 will be relatively straightforward. So 22. Now, of course, whenever you're looking at these, I think it's good to think, is this going to be, how complicated is this integral going to be? It's good to try to develop like an intuition for like when looking at something, am I expecting a really complicated integral, complicated calculation, or am I expecting an easy calculation? So, okay, let's examine one of these slices. Is it a washer or is it just a disc?
Yes.
Just a disc. So let's examine one of these discs. Here you go, Trenton, for you, bro. I'm gonna draw the disc inside the picture. That's your value. Okay. Now, if that makes sense to you, great. If not, you can draw it out here. In any case, we want to ask, what we want to ask is, what's the radius of one of those discs?
Wouldn't it just be the,
It would be 3 if you happen to be looking at the disc at the equator, that's true.
wouldn't it?
But just generally,
The,
consider a point right there.
what's it called, the function?
It would be the x value of this point. Right?
Yeah.
Or let me show you that thought process I was referring to a few minutes ago. Look, examine this disc. We know if you're having trouble getting from the problem statement to like this picture, that is actually a pretty big issue. I probably have to maybe meet with you individually to sort that out. There might be some confusion going on. Just spatially maybe, but hopefully we're all okay with that, right? Just imagining slicing this thing into a bunch of little horizontal discs, and that corresponds to revolving around the y-axis.
Mm-hmm.
If that is still confusing you, please just come see me. I'll try my best to help you understand it. But anyway, so the next step is to go, well, this radius here is just the x value of any point on the curve. So then I look at my expression or my equation and I say, well, how do I write a formula for the x value of one of these points? Given that the curve has this, solve for x. Like that, right? We understand?
Mm-hmm.
So that's the radius then. So any given disk has an associated x value, which tells us the radius, and so the radius is the square root of 9 minus 9 y. Okay? So what's the volume of each disk? Pi r squared. That's the area of a disk, right? That's the surface area of the top, and then you multiply that by the thickness of the disk, because the thickness, of course, is dy. And then I got to integrate. Bounds of integration.
0. Oh, it's one.
Go.
Negative 1 and 1.
Negative 1 to 1. We see why?
Yeah.
Look at where the first disk is. Well, technically there's not a first disk, but the earliest disks, right? There's disks down here. What kind of y value do those disks have? They have a y value of close to negative 1. And how about disks at the top? They've got a y value like positive 1. Yes.
Can you do like 0 to 1 and then multiply it by 2?
Yeah, so this question does say find the volume. So a good practice is to start with this as your first step. Like also, for example, like it's really good to show this. We all know that when you square this radical, right, the radical is going to go away.
Mhm.
But you want to show this. This shows how you set it up. And then your next step, we could do what Alyssa suggests, which is to say, well, firstly, I know by symmetry that this, I could go from 0 to 1 and then double. Right? Makes sense?
Yeah.
And then, I mean, I could also take the pi out while I'm at it, right?
Yeah.
So move the pi out and also double it. So it's 2 pi out here now. And inside I've got 9 minus 9 pi squared. 2y. And so then answer the question from the very beginning. Is this an easy integral or a hard integral?
Easy.
Pretty easy. So no u prime, no u substitutions necessary, nothing wacky. It's just basically a quadratic form there. And we're just plugging in 0 and 1. And it's not even going to involve any fractions. So sort of a trifecta there. So an integral of this is 9 minus 3 cubed. Okay, let's plug in 1. What do we get if we plug in 1? 6. Plug in 0. 0. So, very interestingly, you get an integer multiple of pi, which is kind of interesting. Okay, so I wanted to go over one last thing, which is it's not super difficult or anything. Maybe 24.
What about 26?
I'll cover that.
24.
Or no, I'll cover it tomorrow. But I wanted, if anyone wants to try it out, it's an interesting problem to try it on your own. Just if you can figure out what it's about, that's interesting. So the bottom one might actually be more obvious what it's talking about. But okay, let's look at 24.
Yay.
So 24 says, I've got this region. This region is bounded by y equals square root of x, y equals 0, and x equals 4. This is 4. While we're at it, what's this y value?
2.
2. So this first one says, what if we revolve this around the line y equals 3? So this region here is S. Revolve it around y equals 3. So y equals 3 lives up here. And we're going to revolve this region around that line. Okay, so think about the cross sections. Think about what, if you can visualize the shape, that's awesome. If not, that's not the end of the world, but hopefully you can visualize the cross sections, right? What are the cross sections? Washers, good. It's kind of like what is the outer, I mean, we can just describe this shape. I mean, what's the outer surface of this shape? It's a cylinder. So it's going to form, if I draw it in the same orientation, it's going to be cylindrical and exterior. And then this is going to have, at the bottom, there's going to be a circle inside there. You sort of under, well, I didn't draw a very good picture, but hopefully you get the idea. So, a wormhole or something.
Yes.
Okay, so what you're going to do is let's examine one of these washers. So let's slice it. What is the outer radius? What's the outer radius of this thing? 3? Does everyone agree? Yeah. So it's the distance from here to here. That's always going to be 3 because this is a constant function. So 3. And then what's the inner radius? So be careful. It's a changing value. I heard someone say 3 minus. 3 minus root x. Very good. So 3 minus root x. Do you feel okay about that for the inner radius?
Mhm.
Okay. So and then of course the thickness of this disk, this washer, is dx, which of course clues us into the fact that I want these to have x's in them. And so, anyway, what's the integral? The volume, so 5 times 3 minus, don't be forgetting the
3 squared.
So 3 squared minus
3 squared. Yeah.
So this expression represents the thickness of a single disk. If we integrate, bounds of integration?
0 to 4.
0 to 4, because I'm moving horizontally. And there you go. That's it. We can certainly simplify this. Pull the pi out. So something interesting that happens here. Do you guys see it? Well, maybe it's not obviously interesting, but like you get this 3 squared, and then you're going to minus a 3 squared. So that almost makes you think, wait, does the 3 just disappear? Is the 3 irrelevant? You guys understand or do you agree with my algebra? It's not a sure, it's either you do or you don't.
Yeah.
I agree.
I agree.
So is the 3 irrelevant? That's the question. Is the 3 not, like, could I have made this y equals 5 and gotten the same answer? Huh? For the volume, yeah.
No, it's still relevant.
Yeah, it's relevant. I mean, you can imagine like,
Because it will be.
I mean, you also.
it would be a
like
bigger
the-
shape.
It's, yeah, it's a, even if you subtract, yeah, it's a 6 for X.
Yeah, the 3's inside there.
Yeah.
So if that had been a 5, a y equals 5, you'd still have a 5 squared canceling out a 5 squared, but then this would be a 10 root x.
Yeah.
So, and then just visually speaking, if you make this I mean, obviously this is sort of like a ring, chord sort of. That small ring, and you've made it way bigger, it's going to have more volume. It's going to take more material. So.
Yeah.
Okay, let's do it the other way now. So part B asks, can we revolve this around the line x equals 6? Okay. All right. I'll leave that on the board. I think we have enough room to do it. Same drawing, but this time we're going to slice it. So here's 4. This is still 2. This time we've got, this is our rotation axis. So draw the region. I hope you understand why I'm making them horizontal shadings. This is revolving around x equals 6. We feel okay about that, the drawing? And then the overall shape is going to look, if I try to draw it, imagine that thing revolving around. The base would be, huh?
It's gonna be this with an O, but this no. You're not wrong.
It would look something like, it kind of reminds me of that little illusion where you put the penny in.
Yeah.
So there's this cylindrical hole through the middle, and there'd be a, I don't know, this is my best attempt at a drawing. Kind of like a truncated dome shape with a cylinder cut through the middle.
Yeah.
Understand?
Mhm.
Okay, so then let's look at a slice. So I'm going to draw a slice of this thing. So okay, thickness of the slice, dy. Let's look at the inner radius. What's that inner radius going to be? It's always 2. Do you understand that? No matter where you draw your slice, the inner radius of that rotation is always 2.
Mhm.
And then the outer radius. So just keep in mind, this right here, I'll put it in red. The inner radius is right here. Is that distance.
Mhm.
And then the outer radius is, just taking an arbitrary point.
6 minus y
What's that?
squared.
6 minus, yeah, very good. It's going to be this x value minus this x value. So this x value is always 6. And then this guy's x value, if I rearrange the curve equation, it says this. Do we feel okay about that?
Yeah. Yep.
Yes. I appreciate you trying to keep your eyes open. Okay, so then the volume is pi times the quantity big R squared minus little r squared multiplied by the thickness, which is dx. I'm sorry, dy.
Oops.
And then what are my bounds of integration?
0 to 3.
0 to 2. Because that's my final disk is going to be up at a y value of 2. There we go.
Yay.
Just a heads up, again, with the something to keep your eyes open for is they might simplify this into like, because this expands into 36. When you expand this, you have a 36 minus the 4, 32. This is a bit of a, let us, like on the AP exam, this is one example, or exam. That throws people off. They go, well, where the heck's the 32 coming from? Well, you had to simplify your integrand, so. All right.